Section: Introduction. In this section, we explore the impressive capabilities of large language models, LLMs, in areas like problem solving, knowledge retrieval, and code generation. Despite their advancements, we recognize that these models can still fail on simpler tasks, raising concerns about their reliability, especially in critical fields like healthcare and finance, where errors can have serious consequences. We aim to understand when we can trust LLMs in these situations, leading us to our central question: on which tasks are these models truly reliable? To find answers, we consider existing benchmarks where models perform well, particularly older ones that assess simpler skills. These benchmarks are often overlooked today because many believe that models have reached a high level of performance on them, with remaining errors attributed to noise or ambiguity. However, since we are focused on reliability, we need to determine if models can consistently perform tasks with near-perfect accuracy, even when they appear to have saturated performance. Our contributions include demonstrating that the remaining errors on these older benchmarks are not merely due to label noise and that current benchmarks are inadequate for assessing model reliability. We propose a new benchmarking approach to rigorously measure reliability and begin constructing these benchmarks. To improve noisy benchmarks, we need to update them by identifying and correcting common errors. We define a reliable model as one that can consistently answer questions correctly within a specific task category, given that the questions are clear and unambiguous. This requires well-curated benchmarks where any incorrect answer clearly indicates a model failure. With our newly created Platinum benchmarks, we can now evaluate the reliability of frontier LLMs. We also recognize that within any capability category, tasks vary in difficulty. To pinpoint the reliability frontier, we need benchmarks of different difficulty levels. By identifying the hardest benchmark a model can pass, we can estimate its reliability limits. We focus on mathematics benchmarks, ranging from simple operations to high school level problems, expecting that models will show reliability on easier tasks, which will help us determine the point at which they start to struggle. Section Summary. In this section, we highlight the unreliability of large language models, LLMs, on simpler tasks despite their advanced capabilities, emphasizing the need for rigorous benchmarks to assess their reliability. We propose creating Platinum benchmarks that accurately reflect model performance by correcting label errors, allowing us to better identify the reliability frontier across varying task difficulties. Section: Findings. In this section, we report our findings regarding model errors on revised benchmarks. We present the number of errors made by each model and compare these to the original benchmarks before our revisions. We carefully reviewed all model errors during our revision process, ensuring that the failures we report on our Platinum benchmarks are accurate. Our main findings indicate that reliability issues are widespread. Almost every model makes basic mistakes across nearly all datasets, except for some straightforward math datasets. It is concerning that these advanced models, which are evaluated with PhD-level questions, still make such simple errors. We provide examples of these failures in the appendix. We also found that many saturated benchmarks are too noisy for reliable evaluation. Our analysis shows significant differences in error rates between original and cleaned benchmarks, with many original errors stemming from mislabeling or poorly constructed questions. For example, around 75% of errors on the original SVAMP benchmark are due to these issues. Logic datasets show few errors, but this is because they were generated programmatically. Moreover, we observed that more capable models tend to be more reliable. For instance, GPT-4o outperforms GPT-4o Mini, and Llama 3.1405B Instruct is better than Llama 3.170B Instruct. Notably, the more capable models achieve perfect scores on some benchmarks, while the least capable models do not succeed on any. We also found that reliability varies based on specific capabilities. The O1 series and DeepSeek R1 show the highest reliability in mathematics, while Claude 3.5 Sonnet, October, excels in common sense reasoning. This highlights the need for diverse reliability benchmarks, as different tasks may require different models. By analyzing model errors on Platinum benchmarks, we can identify new patterns of failures. We discovered two specific patterns of questions that consistently lead to reasoning breakdowns in frontier LLMs. We initially identified these failure modes by examining the reasoning processes of models on our Platinum benchmarks and confirmed their consistency by creating similar examples. We detail these failure modes further in the appendix. We also discuss the life cycle of benchmarks, noting that they typically undergo development, progress, and eventual retirement when they become saturated. We present accuracy data for various math and science benchmarks that illustrate this life cycle. Regarding benchmark processing, we outline additional cleaning steps for certain benchmarks. We utilize a chain of thought prompt for evaluation on all datasets except for VQA v2.0, where multiple reasoning steps are generally unnecessary. The specific prompts vary slightly, but we maintain a consistent format for open-ended and multiple-choice questions. For open-ended math questions, we instruct models to respond with an integer and avoid extra formatting, as they often use LaTeX styling unnecessarily. We find that models rarely engage in step-by-step reasoning for simple visual questions, even when prompted to do so. Finally, we identify patterns that lead to frequent model failures. By examining the reasoning processes of models on simpler tasks, we gain insights into why these failures occur, particularly through the two identified patterns that consistently result in reasoning collapses. Section Summary. In this section, we report that reliability challenges are prevalent across various models, with most making simple errors on complex tasks, despite their advanced capabilities. We also identify specific failure patterns in reasoning and emphasize the need for diverse benchmarking to select the most reliable models for different tasks. Section: First Event Bias. In this section, we examine the first event bias in model failures on the drop reading comprehension dataset. We found a specific instance where several large language models, LLMs, failed due to a reasoning error. The question asked what happened second between two events, but each model responded with the first event and even noted that it was the first. To explore this issue further, we created 50 additional examples in a similar format. We used GPT-4o to generate a context about a historical topic with a sequence of events and selected two events with a clear order. To eliminate bias from the event order in the questions, we flipped the order for each example, resulting in a total of 100 examples. We discovered that three models, Gemini 1.5 Flash, Gemini 1.5 Pro, and Mistral Small, failed on over 85% of these examples, while random guessing would yield a 50% success rate. Other models showed at least a 25% error rate, whereas the median error rate on the overall drop benchmark was below 3%. Next, we looked at rounding errors in models like Claude 3.5 Sonnet. We found instances where it rounded up answers after a division, even when the result was already a whole number. We noted that the solutions to these questions had few divisors, which led us to investigate if this rounding failure was linked to how close the solution was to being prime. We created 3 examples similar to a bus question that required only one division. We randomly selected values for the number of people and measured the average number of failures based on the number of divisors. We found that the fewer non-trivial divisor pairs a number had, the more often this rounding error occurred. During our review, we also identified label errors in 15 different benchmarks. We present examples of these mislabeled or poorly written cases across various benchmarks, including mathematics, reading comprehension, and visual question answering. Finally, we highlight some simple question types where frontier LLMs still struggle. We provide examples of model failures from the revised benchmarks to illustrate these issues.